Mithilan, are you able to hear me?
Yes, sir.
Yeah, we were doing those textbook problems, no? Any doubts from that? Okay. So just to begin with the momentum, we'll start with few more problems. Nithilan, today you might not be able to see me, okay, because the laptop is on the other side. Wherever I'm showing demonstration, I'll switch on the camera.
Okay.
Okay. Sanjeevan, are you able to see? Is it clear? If you want, you can slightly move this. The other room is also occupied today. Yes. So I want you to try 6.3. So there is a long solenoid with 15 turns per centimeter. Okay. So what is the given value? 15 turns per centimeter is what? Which n? It is small n. So small n is 15. That is per centimeter. Has a small loop of area. So area is how much? So 2 into 10 power minus 4 meters square. Placed inside the solenoid, normal towards axis. If the current carried by the solenoid changes steadily from 2 ampere to 4 ampere in 0.1 seconds. Centimeter, no? Centimeters. But 1 centimeter is 10 power minus 2 meter. No? So 2 into 10 power minus 4 meters square. So there is a steady increase in the value of current from 2 ampere to 4 ampere, which is happening in a time duration of 1 second, 0.1 second. Now, what is the induced EMF in the loop while the current is changing? So how do you think? Mu naught into small n into I. Yes. Yes. Not 90, theta 0. So if at all I have to frame a formula for this problem, how does it look like? EMF is equal to change in magnetic flux divided by time. So change in magnetic flux is B final, A final, cos theta final minus B initial, A initial into cos theta initial divided by the amount of time. So here B final and so B final is mu naught n into I final. Area is A only. Cos of theta is theta only. That is 0 degrees. Minus mu naught into small n into I initial into area into cos of same 0 degrees divided by the time is 0.1 seconds. So if I take out mu naught into n into A outside, mu naught into n into A divided by 0.1. So I final minus I initial is what is taken. So how much is this? 4 pi into into 15 per centimeter. So 15 divided by 100 into area is how much? It's because of my sweat. So area is 2 into 10 power minus 4 into I final minus I initial is how much? 2 The whole divided by 0.1 is 10 power minus 1. So when you substitute all these values, everything is in terms of SI units. When you substitute all these values, the value of EMF is what you can calculate, which will be in terms of U volt. Yes. Nithilan, are you able to understand?
Yes.
Good. So Ritika, are you there? Not sure. She has not yet joined. EMF is, I don't know how much volt you will get. That's the answer. Those many volt is the answer. Tell me. How much 2 into 240 pi into 10 power minus 10 now? That's fine. Is it that's minus? No, I'm asking the value is very small. I'm not saying your calculation is wrong. 2 pi into 240 pi, no? So negligible value. Just check what is the back answer. Adan, 240. That's right. What you did is almost right on the same. First 2.4 into 3. 3.15. So it'll be 2. Yeah. Approximately, you can take it as 3 into 10 power minus 10 into 10 square. I wrote 240 as 2.4 into 100. So 7 point something into 10 power minus 8. I converted to meter, no? By 100 I wrote. You didn't take this 100 into consideration. Is it? Okay. So calculation part, now you can do it later. See, this chapter, it is all about how you solve problems. So be careful. Okay. Yes. So from yesterday's class, we discussed an important topic called motional EMF, and we saw a problem also based on it. Then we did some problems based on Lenz's law as well, right? Now what we can do is, we will try to do this problem. This is a very, very, very important one, at least according to me. I'll definitely ask my tests. 6.8. There are a lot of concepts. That the diagram is similar. Yes, it's a problem based on motion EMF, which is very good. That is into the plane, and this is out of the plane. The arm PQ of the rectangular conductor is moved from x is equal to 0 outwards. So read the question carefully. There is a magnetic field existing only for certain region. It is not existing throughout. In that certain region, one of the points is considered to be x is equal to 0 and the other point is considered to be x is equal to b, which is actually the end point of that magnetic field also. In that, what you have is a rectangular framed metallic channel on which there is a conductor which is able to freely move. And the conductor, in which direction is it moving? It is moving in the outward direction. So it is moving in the outward direction in such a way that when it is moving, during the course of its journey, there are some places where the magnetic field is increasing, and after a certain point, it becomes a constant. So look at the motion, guys. So they are saying the arm PQ of the rectangular conductor is moved from x is equal to 0 outwards. The uniform magnetic field is perpendicular to the plane and extends from x is equal to 0 to x is equal to b and is 0 for x greater than b. Only the arm PQ possesses a substantial resistance of small r. So PQ has a small resistance of small r. Consider the situation when the arm PQ is pulled outwards from x is equal to 0 to x is equal to 2b. Okay, what are we supposed to find? Consider the situation when the arm PQ is pulled outwards from x is equal to 0 to x is equal to 2b, and then it is moved back to x is equal to 0 with the same constant speed b. This is where the challenge comes. Now our job is to obtain the flux, induced EMF, force necessary to pull the arm, and the power dissipated as joule heat, and you need to sketch the variations of all these quantities with the distances. Okay, shall we try to understand how it works? Now tell me one thing, when it is moving from x is equal to 0 to x is equal to b, okay, when it is moving from x is equal to 0 to x is equal to b, magnetic field is increasing or decreasing? Increasing. Either the amount of magnetic field associated with the loop is increasing, area is increasing. So I can say flux is increasing. After point B is equal to 0 to B is equal to 2B or x is equal to 2B, what is happening? It is a constant. So the flux is going to increase from 0 to B and it is going to be a constant from B to 2B. Right? So flux, I'll break the journey as, observe this, I'll break the journey as x is equal to 0 to x is equal to B. So what is going to happen to the flux? So flux will be equal to, can I write it as B into A into cos of 0 degrees? I'll take it as 0 because it's a rectangular loop. I'll take the direction of magnetic field and the area vector to be the same. So B is B only. What about the area? This is the length L, and if I take this distance to be x, so it is going to be Lx into cos 0, that is going to be 1. This is the value of flux, which is actually acting as a function of distance. So you see, they told sketch the variation of these quantities with the distance, means x-axis is supposed to be taken as the distance, and y-axis is flux, EMF, all other quantities. So from x is equal to b to 2b, what happens to the flux? It is b into a into cos 0 degrees. Magnetic field is b. Then what about the area? Area is L into B. L into B, I didn't write it as L into 2B. Yeah. Because B is the area, region across which the magnetic field is existing. I cannot take the bigger area into consideration. Okay, so B into L into B into cos 0 is obviously going to be a 1. So the same thing happens when the conductor is returning from 2B to B and again from B to 0. But the only difference is going to be, it is going to be a negative value. That's it. That is a scenario. Then if I take a graph like this, if I take flux as a function of, there is something. So if I take the flux as a function of displacement, when x is equal to 0, flux is 0. So x is equal to b is a checkpoint. X is equal to 2b is a checkpoint. Again b is a checkpoint. Again 0 is a checkpoint. So from 0 to b, the flux is increasing because flux is equal to what? B into L into x. So flux is directly proportional to x. So it is following the format y is equal to mx for. From b to 2b, it is a constant. From 2b to b, it is a constant. And from b to 0, again it is decreasing. Is that right? So this is what happens. So this is the variation of flux as a function of distance. Okay. Please make a note of this. Right. So after this, what are we supposed to find? Read the question. Find the EMF. So EMF is equal to, listen to this carefully. Yesterday when we did the problems, right, we always found the magnitude. But what does the mathematical expression say? It is minus n into d phi by dt. Why did I take d phi by dt here? Is because there is an instantaneous change taking place as the distance is changing. So again, from x is equal to 0 to x is equal to b. Okay. So what is the EMF? It is minus, the number of loops is only 1 into d phi by dt. So phi is equal to b into L into x. 1 into d by dt of bl into x. So minus of bl into dx divided by dt or minus bl. It is minus b into L into b. So minus, you should not leave here because you're drawing a graph. Again, when you take from x is equal to b to 2b, what happens to the EMF? It will be 0 because it's a derivative of a constant. Correct? In the line would a derivative. So line parallel to x-axis, its slope is 0. Again, from x is equal to 2b to b, and from x is equal to 0 to x is equal to b, it will be b into L into b. This is irritating. No, we should not have a problem. Yes. So EMF is 0. So here EMF will be equal to B into L into V, right? So when you try to plot the graph, between EMF and displacement, EMF is minus BLB from 0 to B, and from B to 2B it is 0, and from 2B to B again it is constant. So that's why you will have a box kind of thing, where that line is actually, so the dotted lines are actually not taken into consideration. They're only to represent the region. I hope it's clear. Then what else is the next question they're asking? Induced current is asking. Induced current they are not asking. Okay, they gave the resistance of the conductor, right? So I is equal to E by R. Nithilan, are you there?
Yes, sir.
Good. You're able to understand now?
Yes, yes, right.
Yes. So I is equal to E by R, right? So I, when you calculate I, how do you calculate the force? So first of all, when current is flowing through a conductor and the conductor is placed in the presence of external magnetic field, what will happen to it? It starts experiencing force of a value B into I into L. What is the value of B? B only. I is E by R. And L is the length of the conductor. Is it clear? So B into, what is the value of E? BLB divided by small r into L. So you will get B square L square B divided by R. This is the force experienced by the conductor. So how much force are we supposed to apply to ensure that it is pulled? It is almost the same force, right? It's almost the same force, but with a reverse direction. So how is the graph for this? Between x is equal to 0 to B. So it will be minus B square L square B divided by R. B to 2B, 0. So when you draw the graph, how is it going to look? Force this, yes. Except the fact that the values are different. Minus B square L square B divided by R. This is B, this is 2B, again this is 0. That's it. So this magnitude is also B square L square B divided by R. Is it clear? And lastly, what are they asking? The power dissipated. What is power? I square R. Power is I square R. They ask the power or power? B into I. B into I, B is equal to I R, I square R. So I square is how much? B square L square B square divided by R. R square. B, see, EMF is BLV, no? By R, the whole square into R. So this will be B square L square B square divided by R. Because it will become R square into R, this and this will get cancelled. So it will be B square L square B square divided by R. Is that right? So when this is the scenario, what can I say? So this is power, this is the displacement. So B square L square B divided by R from 0 to B, and from B to 2B, and from 2B to 0, again it is B square L square B square by R. So here none of the values are negative because it's a square. That's it. So this is how, if you see, they would have drawn everything in the same graph. But I didn't have a place, so I had to write it like this. Am I clear? Right. So this is another important concept, which is a problem based on motional EMF. Okay, eddy currents, I'll explain it later. Now we'll move to the next important concept that is called as inductance. Okay, shall we discuss what it is? Right. Listen, I have some questions. Okay, if you have a device which is able to resist the current, what do you call the devices? Resistor. So I repeat it again. If you have a device which is able to resist the current or oppose the current, you call it as a resistor. And the property it possesses is called as resistance. Resistivity, resistance. Okay. Similarly, if you have a device which can store charge, you call it as a capacitor. It has a prefix of OR, and the property it possesses is called as capacitance. Then, if you are able to think of a device that does something, what it does, I'll talk about it later. Then, if you have a device which does something called as inductor, okay, then the property it possesses is called inductance. That is called. Okay. So before I start this, I want you to have 2 points in your mind. One is about the Faraday's law of electromagnetic induction and Lenz's law. Have it clear in your mind. So what do they speak about? Faraday's law speaks about the fact that if there is a change in magnetic flux, magnetic flux. If there is a change in magnetic flux, then you can think of EMF getting induced. Lenz's law says the induced EMF or the induced current will be in such a way that it opposes the cause. Right? Having these 2 points in mind, let's think of a fact where I'm able to take a wire. Okay. Generally, if you take a wire, every wire in this world every wire which carries current is called as a conductor. But every conductor in this world will have some amount of resistance associated with it. If I take that wire and instead of taking it straight, had I put it in this kind of windings, right? Where instead of having an open segment, I have curvatures or closed segments so that I can define something called as area associated with it. And I can think of the magnetic field associated with it. Okay. This is the tricky part. Listen to this carefully. If I take a coil which is wound in this format and what am I going to do? I'm going to connect it across a battery with the help of a switch. Now, is the current going to flow through it? Obviously, no. When I close this, what will happen? When I close this, current will start flowing through the coil because the circuit is completed. Right? As soon as I close this, can I say, let's say the steady state current that is flowing through the conductor is I. So initially, before the key was closed, what was the current flowing through it? 0. So to reach the steady state value I, it takes some time. Not like it is instantly, like it's like a car only. As soon as you accelerate, it's not going to have 100 kilometers per hour. It takes time for things to get updated from 0 to some steady state value, right? So when that happens, then observe when the current is flowing through this coil. Can I see magnetic field is induced in it? It is something similar to a solenoid. I'm not calling it as a solenoid, rather I'm calling it as a coil with some bends. So if I take this coil, then there is some magnetic field associated with it. Accept it. Right? So I want you to answer this question. If the current at the top is into the plane and the current at the bottom is out of the plane, when I see it from this side, what pole am I able to see? Because current at the top is into the plane. and at the bottom it is out of the plane, you call it as North Pole. Nithilan, this is an important point. I hope you understood this. You got it right? This is North Pole. So when one side is North Pole, the other side will be a South Pole. Right? Then what is the direction of magnetic field? It is from north to south outside the magnet and south to north inside the magnet. Can I say that there is some magnetic field linked within the coil? Yes. Right. Now, when there is a magnetic field linked within the coil, can I say there is some flux also associated with the coil? Right. Now, I need to answer a question to speak about induced EMF, whether this value of flux is changing or is it a constant. So, between the time it started, that is between 0 to reach that steady state value, what has happened to the flux? It has increased, it has changed, right? Can I say that the change in flux that has taken place with respect to time is directly proportional to the rate of change of current? Can I say that? Are you convinced or not? Right? And what does that I stand for? I is the current which is flowing through itself. I is not, see, till now we would have seen we have a magnet separately, we have a pickup coil separately. But what are we having here? We have only one coil, and that coil is generating magnetism. And due to its own magnetism, there is a change in flux taking place because of the increase in the value of current. Is it right? Right? So can I say that the change in flux that is taking place is happening due to whom? Due to the change in the value of current that is taking place. So to be more precise, instead of writing this directly, what I would try to tell you is, I would like to say if the coil has n number of turns and the magnetic flux associated with it is phi b, then I will say the amount of the total flux that is associated with it is directly proportional to the amount of current that has got increased, where I is its own current. Now, when I differentiate this on both the sides, what do I get? N into d phi b divided by dt is, okay. But before that, I need to write another point. Now, can I say N into phi b is equal to some constant times I? So that constant, I'll call it as L, and it is called as L times I, where this L is what is called as inductance. Okay. Now, if you differentiate this on both the sides, are you guys convinced with this fact? The total flux that is linked with the coil is directly proportional to its current. Means if you're decreasing the value of current through it, flux will also decrease. Okay. Reverse of it. Right. So if I differentiate on both the sides, d by dt of n into phi b is equal to d by dt of L into I. But what is d by dt of n into phi b? It is n into d phi b divided by dt is equal to L is a constant. Inductance of a given material, like how resistance and capacitance are constant, inductance is also constant. L into di divided by dt. And what do you call this n into d phi by dt? This is what is called as the EMF, but with a negative value. So EMF will be equal to minus L into di by dt, where the L is what is called as inductance. And to be more specific, it is called as self-inductance because the change in flux is happening due to its own current. Is that clear? And this L is what is called as inductance. I told you it does something. What that something is, I'll explain it now. But before that, copy this. Now, if I don't write north and south pole, you will not be able to realize that magnetic field is there. There, but you should have known which direction. Maybe that is also one extra point I wanted to. Inside could be south and north, but you should be able to choose which is south and which is north. How will you know? I never spoke induced EMF. I have not yet spoken about induced EMF. I didn't tell you which one is positive polarity and which one is negative polarity. Which one? Repeat it again once. Okay. But I'm thinking that north and south pole are the induced poles. What you are thinking? They are not induced poles. They are the naturally occurring poles because of its own current. There is an induced EMF which will try to oppose the cause. I never spoke about the induced EMF. That has a special name called as back EMF. I've never spoken about it. Is it clear till this point? So minus L into dI divided by. So L will be equal to E divided by dI by dt. Magnitude. Okay. So L into dI by dt. Sorry, L is equal to E divided by dI by dt. Now I have something to say. We know this R is equal to V divided by I. Means R is what? Resistance is inversely proportional to current. What does it mean? Means if the resistance increases, current will decrease. Or can I say resistor's job? Resistance is the property term. If the property of resistance increases, the amount of current flowing through it decreases. Can I put it in this way also? Resistor's job is to oppose the current because they are inversely proportional. Then, with the same logic, what does an inductor do? Opposes the change in current. It is not, we are not always concerned about increasing or decreasing. We are only concerned about change in current. So, inductor will always try to oppose the change in current taking place because it is a very important one, right? Half of them, when I ask the question, what does an inductor do? It induces current and all. It has nothing to do with inducing. Inductor is also something similar to a resistor, except the fact that resistor will oppose flow of current. Resistor will oppose flow of current. Inductor will oppose the change of current. It will not allow the current to change through it. Meaning, inductor will never allow alternating current to flow through it easily. Because alternating current, what does it do? It changes the direction with respect to time. So inductor will always try to oppose the alternating current. Means it will not allow the current to change at all. Is the point clear? So, yeah. Now, having said this, what is going to be the SI unit of inductance? SI unit will be volt divided by ampere per second. So can I write it as volt second per ampere? Right? This volt second per ampere is what is called as Henry, which is the name of a person. That is why the symbol is capital H. So if you remember one thing, we would have told that the capacitance values, farad, capacitance with the unit farad, farad is generally higher. That is why when you see no capacitors are generally designed in terms of farads. They are mostly designed in terms of microfarad. In a similar way, Henry is also a slightly bigger unit. So most of the inductors are not designed in Henry, they are rather designed in millihenry. That is why you see most of the questions related to inductance, you will have all the questions as millihenry, and all the questions with respect to capacitance will mostly be in terms of microfarad. Millifarad would occur, it will be only in terms of microfarad because the unit is that big. It's practically not possible to handle it. So am I clear to this point? Right? So secondly, we should know the fact that inductance is also a scalar quantity, and try to write the dimensional formula. I'll give you a minute time. Try to write the dimensional formula. Can I rub this for inductance? So write current in terms of write EMF in terms of known parameters and then proceed. Write the dimensional formula of inductance. The FL square PQ. So how do you write current? How do you write EMF? But volt is not one of the 7 fundamental quantities. When you write the dimensional formula, it should be in terms of all the fundamental quantities. Mass I into R is dimensional formula. Instead, why don't you think it in terms of potential difference is work done per unit charge? W by Q la. Other you see work done you know kilogram. So first write down the unit, then convert it to. So E is equal to W by Q da. W is what? Kilogram meter square per second square. And what is Coulomb? Coulomb is ampere second. If you convert it to dimensional formula, then what will happen? M L square T minus 3 A minus 1. This is the dimensional formula of EMF. Divided by, what is the dimensional formula of current? A. Divided by time. So take it to the numerator. What will happen? ML square T minus 2 A minus 2. B is not a power. That's what that was. So always try to write down the formula which you are comfortable with. These things mostly come for competitive exams. You should know them. 4 marks is the plan. Where do you want to leave? Is it clear till this point? Okay. Now, we'll discuss about, I'll just give you the introduction of mutual inductance, then how to calculate the value of mutual inductance between coaxial solenoids that we'll see later. Okay. So till now, whatever we saw was related to inductance. Inductance is another name for self-inductance. I hope you got the answer for why we call it as self-inductance. Right? Why do we call it? Because the EMF is induced due to the change of its own current. Right? Then what about mutual rights? This term you would have learned last in your 10th grade. Mutual inductance in particular. So mutual means what? There are 2 neighboring coils. If one is able to create an impact on the other, we call it as mutual parameters, right? So here what is happening? In the previous case, the change in current due to the coil induced EMF in itself. Whereas here, if I have two coils like this, okay, which I'll call it as 1 and 2. In these two coils, you will have one of the coils which is connected to a battery. And you will have one of the coils which is connected to a galvanometer. So the one which is connected to the galvanometer is generally called as a pickup coil. We know this fact. The one which is connected to the battery is called as the magnetic source. Right? Now the fact is, whichever is connected to the battery is more technically called as a primary coil. And the one which is picking up the mutual inductance is generally called as the secondary coil. The one which is connected to battery is primary, and the one which is picking up the EMF is called secondary. Now, if I close the switch, what will happen? There will be a magnetic field induced here, and due to this magnetic field, so initially what was happening is there was no flux linked with both the coils. Whereas when you close the switch, this flux will get linked with the second coil also, provided they both are very close to each other. Most importantly, you will not place them side by side. You will place them along the axis, something like this. One will be a bigger coil and one will be a smaller coil. So these two coils are said to be mutually coupled. So you can say that these two are mutually coupled. Okay. So are you able to understand? So out of which you have two coils. No? For every two coils, that you can say one is primary and the other is secondary. But you should know the fact that which one is primary and which one is secondary. Which is primary? Whichever is connected to the battery source is primary. Whichever is picking up is called as secondary. Okay. Now, can I say if the primary coil is induced with, or the primary coil is given some current, it has a magnetic field, and if that magnetic field also gets linked with the secondary coil. When this is happening, as long as the change is taking place in the magnetic field in the primary coil, there will be a change taking place in the secondary coil also. So unlike the previous case, what we can show is the amount of flux which is linked with the secondary coil is directly proportional to the amount of current passing through the first one. So in the previous case, what did we write? The amount of flux that is linked with the coil is directly proportional to its own current. Whereas in this case, the flux that is linked with the secondary coil is directly proportional to the current that is passing through the first coil. Right? Now, if I remove the symbol N252, this I can call it as M21, where this M21 is called as mutual inductance of the first coil with respect to second. Mutual inductance of the first coil with respect to second is what is this value. Is that clear? Right? Now, similarly, if I swap the primary and the secondary coil, what can I say? Then N151 will be directly proportional to I2. That is a pattern. So N151 will be equal to M21 I2. I think I made a mistake. It is M12, no? M12 I2. So how to remember that is, when you write M12, no, you will get N151 divided by I2. So you need to choose the number in such a way that the numerator value will come first, denominator value will come next. They will be the same provided the length of the coils are the same. If not, they will not. That is what we will be seeing as a proof. Okay, that is a slightly tricky part. I want to give you some time to absorb it. Is it clear? This is what happens. It is for your information. See, the notations is only for our concern. Just to not get confused about it. Either. That is what we do in the derivation. We keep swapping. If in the derivation article, it's actually a solenoid. So they take two long coaxial solenoids and they try to find M12 and M21. That is when we will try to come to a conclusion that M21 and M12 are the same, provided the length of both the solenoids are same. This is a derivation actually, example of this one. But in real-time basis, what will happen is M12 and M21 need not be the same. It depends on how many windings are there here, how much current is passing, all those things are taken into consideration. One to just a notation. Notation. For the very system, what will you do? You will take one thing. If you are writing some experiment tomorrow, one paper will get confused. They wanted to bring in a proper analysis. Is that clear? So similarly, if you observe, what does M12 and M21? So what is going to be the SI unit of M12 and M21? So there is one more step that we can do, right? There is one more step that we can do, I'll tell you. That is, I wrote N252 is equal to M21 times I1. Can you differentiate on both the sides? N2 into d52 by dt is equal to M12 into di1 by dt. So this is again minus E is equal to M12 into di1 divided by dt. So M12 of N over minus E divided by di1 by dt. It is the same. So volt per ampere per second, which is also taken into consideration as Henry. Is it clear? So this is all about mutual inductance and self-inductance. Also, we saw a problem based on motion area. So I want you to revise to this topic and come. Yeah, now the derivation is complicated. Okay. So after this, I think we're almost done with the chapter. Maximum eddy current then I need to explain you about AC generator, but I have to check if AC generator is there or deleted. Even if it is deleted, I have to explain because that is a connection for next chapter. Then I will not understand why those equations are actually confusing. So I will explain that also. Maximum 2 more classes will be done. AC will take some time, right? It's a very big chapter. Then again, electromagnetic waves is small. So this clear, no? So that's it from my side. Nikhil?
Sir?
Yeah, are you clear?
Yes, sir.
Okay, then we'll wind up.
Thank you, sir.
Which test?